So we have learned for any condition, the momentum is conserved. We have momentum conservation. So we just need to build one equation to solve that. And for us, most of the time we're only going to dealing with one-dimensional condition. So we have, and we usually only have two objects. So we have initial momentum m1v1i, m2v2, that's initial momentum, add up together, this is pi, and then you have final momentum. This is how we solve it. You just build this equation, m1v1i plus m2v2i equals m1v1f, m2v2f. So usually for us, we just build this one equation to solve a condition problem. Now for example, this example, you have object 1, 3m, object 2, m, initial velocity v0, initial velocity 2v0. Now we know the final velocity of object 2. What would be the final velocity of object 1? So we build momentum conservation equation, break it down, plug in all the numbers, m1 3m, v1i v0, m2m, v2i. Now this time, because we choose right to the right to be positive x, so initial velocity of object 2 is negative 2 v0. Final velocity of object 2 v0, we need to solve this. You have one equation with one unknown variable. You just need to do an algebra to find it. And then it asks you what would be the change of kinetic energy for this condition. So you just calculate the initial kinetic energy of the system. What would be the initial kinetic energy of the system? Ki 1/2 m2v0 square plus 1/2 3m v0 square. Kf is 1/2 3m 0 square plus 1/2 m v0 square. And you kick it out, you will find the kinetic energy decreased by 3m v0 square. So what kind of condition is this? Is it elastic condition or inelastic condition? Because there is energy loss, so it got to be inelastic condition. But it's not completely inelastic because these two objects, they don't stick together. And for inelastic condition, there is an equation that we can use. Now these two equations, you probably will need to write them down on your cheat sheet for the next exam. So basically, for inelastic condition, we only need to know the mass of m1, m2, and v1i, v12. That's all. We just need these four quantities. And then we can calculate what is v1f, v2f, the final velocity of object 1 and object 2. Now this is different from this problem we did. This problem you need 5 quantities. 1, 2, 3, 4, 5. And why is that? Because you see, you build an equation. It has 1, 2, 3, 4, 5, 6, 7, 8. No, not 8. This 6 is actually 6 unknown quantities. 1, 2, 3, 4, 5, 6. So if you want to solve this equation with 6 variables, you got to know 5 of them because you only have one equation. However, for inelastic condition, momentum conservation still gives us this 6 variable. Six-variable conservation equation. But we also, from inelastic condition, have this one. So we have kinetic energy conservation, 1/2 m1 v1 squared plus 1/2 m2 v2i squared equals 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Now you have 6 variables, but you have 2 equations, so you just need 5 known quantities. And if you know these 4 variables, 1, 2, 3, 4, and you solve those 2 equations, you'll get this answer. That will be the solution to equation 1 and 2. And how to solve these two I have shown on this slide. So if you're interested, you can just try to follow each of the steps to solve those 2 equation set. Now let's see some special case. Now we have a special case. You have 2 objects with equal mass. Initially, one object at rest. Other object bounce into the object at rest. What's going to happen is that initially this one has velocity v. This one has rest. After the collide, this one will stop at rest. This one will have the same velocity as this one. This one equals this one. So basically it looks like they exchange each other's velocity. And now, because this is inelastic condition, we have this solution. You just need to know for this problem is special m1 equals m2. So you have v1f equals v2i because total mass is 2m, and v2f is v1i. That's it. The exchange velocity. There's a special case. Now for another special case, what happens if m1 is smaller mass, bouncing into object at rest, and the m1 would bouncing back. M1 would bouncing back with a negative final velocity. Now on the other hand, if you have a heavier object bouncing into an object at rest, what's going to happen? They will both move this way after the condition, which all can be obtained using the solution for elastic condition. Now we explain what is gravitational slingshot or gravitational resistance. So you have a spaceship moving toward the planet, for example the Earth. Earth is moving this way. So we kind of have calculated the velocity of the Earth is roughly 30 kilometers per second relative to the Sun. That's the velocity of our planet. And the yearly velocity of a spaceship launching from Earth should be roughly 10 km per second. So planet should have a larger initial velocity compared to a spaceship. The spaceship is moving this way, and planet is moving this way. Now, when the spaceship gets close to the planet, the gravity will tilt it moving direction. It will move this direction at the end. And this can be regarded as a collision problem because there's no external force. The only force that matters is gravitational force between those two, and the internal force. So we can use momentum conservation to solve this kind of a collision problem. Now, on the other hand, there's no kinetic energy loss for this collision because you can safely connect gravitational energy when the spaceship is far away from the planet, and so say there is no energy loss. So you can use a solution for elastic collision. You will find that the final momentum of the spaceship, it will be expressed like this and expressed like this. Now what we need to know is that the mass of the spaceship is much smaller than p. What does that mean? It means this one is 1. This one is -1. This one is 2. See that? So you have the velocity of the spaceship should be 2v initial velocity of planet subtract initial velocity of the spaceship. I already gave you the number. Planet is moving 30 km per second in this direction. So your time 2 is 60. Subtract 10. So after all, a typical spacecraft would move 50 km per second. So initially it's moving with 10 km per second in this direction, but after it collides with the planet, its velocity is 50 km per second. So its velocity is hugely accelerated. And that's why we have those two plots in those two movies that we are going to write a review about. The Martian. So if you, and I think I upload the movie clip of that very smart young student explain this to the director of NASA, which is kind of insulting. Now, you see, because they need to get this spaceship back to Mars as soon as possible to pick up Matt Damon. So they need to accelerate it. Now, if the Earth is moving toward the Mars, so the spaceship can go around the Earth and it accelerated by its speed accelerated by 5 times, so it can get to Mars much faster. And then we have the movie Interstellar. If you watched it, so almost in the end, the spaceship is kind of running out of fuel. They kind of cannot back to the NASA star, which is hopeful. So what they did, they do a gravitational slingshot around this black hole so they can get a much higher velocity to the planet. However, the trick here is that they don't have enough speed to escape the gravitational pull of black hole. So what they did is the Dr. Cooper and the droid just push themselves back this way, so the spaceship can get a higher velocity, so they can escape black hole. So Dr. Cooper and the droid keep sacrificed, so Dr. Brent can go to the next planet using gravitational slingshot of this black hole.